So again, we're looking for this unknown temperature, final temperature. We know we've got a total internal energy change here that might control that. So let's see here. I do know the mass of the copper. I don't know the mass of the water, but I can find it because I do know the volume of the water. So I can find the mass of the water. I know the initial temperature of both the water and the copper, so therefore I should be able to find the initial, U value. Well, let's see. I do know I can convert those into, I can use specific heats to find those. So I can do this. I can say the mass of the copper times the specific heat of the copper. Again, our text uses C sub P for solids and liquids. That's T2 minus T1 of the copper. Plus, then the mass of the water, C sub P for the water, times T2 minus T, and that pins. Done. New pin. So minus T2, times T2 minus T1 for the water. So I know the initial temperature for both copper and the water. I don't know these specific heats. I can go look them up. And we said we should be able to find the mass of the water based off of density of water, assuming it's liquid, and the volume of the water. Okay, so we can knock that right out right now. I've got about 1,000 kilograms per meters cubed. I've got a volume of 120 liters, and if memory serves, there's about 1,000 liters for every cubic meter. So that works out. Right? 120 liters of water has a mass of around 120 kilograms. We'll just keep the mass simple there. Okay. Okay, what else here? We need to go look up specific heats. So we go into our text. We should have property tables towards the back of the text. One of the first property tables, and we're looking for metric units. Here, one of the first property tables, table A. This one's A3 in our text. Table A3. Right? Table A3 has properties of common liquids, solids, and foods. We have over here metal and liquids. Right? So let's do. Actually, we'll go over here first. So we'll go over here. I've got water. Specific heat of water at 0 degrees Celsius, 25, 50, 75, 100, and it's going to start at 422. At 25, it's going to go to 418, and at 50, it's going to stay 418, and at 75, it's going to go to 419. So we're going to be somewhere in this range. So I think 418. We don't know T2, so we got to kind of guess at what it should be. We're going to talk in ideal gases. The guess and check in ideal gases gets a little more interesting, we'll say. But for us here, we'll just say 4.18 is probably going to be a pretty good guess at that specific heat. All right, so let's get properties here. Properties. C sub P for water, we're going to say is approximately 4.18 kilojoules per kilogram Kelvin. Again, we don't know T2, so we can't find an average specific heat because we can't find an average temperature. But this will give us a pretty good guess, I think. C sub P for the copper, that might be a little trickier. Let's see. So over here we've got specific heat of metals. I do have copper up here, right? So you're gonna hear a pop. Okay, I don't know how well you can see these, but I do have copper at 100 degrees is 0.393. At 27 degrees is 0.386. We're going to be somewhere in between those. We're starting at 80 degrees C, and the coldest it's going to get is the initial temperature of the water at 25 degrees C. I don't think it's going to get all the way to 25 degrees C, but so somewhere between 0.393 and 386 is going to be our specific heat for our copper. I think we're just going to say 0.39 is going to be a really good guess for that. And we'll just round to 2 significant figures for an example problem that I'm doing very quickly on a video. I think that's a pretty good guess. Okay, we could probably get a 3rd significant figure if we do a guess and check. If it was a homework or an exam problem, we would try to attempt that guess and check method. Okay, and we'll do a guess and check on the next problem, on an ideal gas problem. But for here, I think this will get us going. So I know now the mass of the water. I know the specific heat of the water. I know specific heat of the copper. I know the initial temperature for both the water and the copper. So I still have one equation here with 2 unknowns. I've got one equation. I don't know T2 for the copper, and I don't know T1 for the T2 for the water. I don't know T2 for the copper, and I don't know T2 for the water. So one equation, 2 unknowns. Can we solve that? Well, what do we know about those final temperatures of the copper and the water? What do you think? Is there you think it's okay to say that those are the same? We okay with that? That makes sense? The goal here is to try to find the final temperature. What's the final temperature? Well, the final temperature is going to be when these 2 substances have reached a thermal equilibrium with each other, meaning they're going to reach the same final temperature. So that's actually what we're looking for, is just T2. So there's no need to differentiate it now. We've established it's going to be the same T2. Page 2. Right. So let's see here. I don't know if I could probably squeeze my algebra in there. But you know what? I got a couple more sheets of paper. Let's just go to the next page, shall we? Okay, so we're looking for T2 then. So I'm going to solve. You saw I'm going to solve this equation right here for T2. Okay. T2, that might be too much algebra to try to do in my head. Let's see here. T2. No, I think I'm okay. That's going to be, I'm going to have the mass of the copper, C sub P of the copper, times T1 of the copper, plus mass of the water, C sub P for the water, T1 for the water. That whole thing is going to get divided then by, mass of the copper, C sub P for the copper, plus mass of the water, C sub P for the water. I think that's okay. I think we could use Celsius temperatures here and probably be okay. I would suggest to you, if you're ever in doubt, just go ahead and use kelvins. This is going to be 298 kelvins. And this is going to be 273 plus 80 is 353 kelvins, I believe. I'm doing those in my head. It's kind of dangerous. But so, when in doubt, use kelvins. I think we could use Celsius here and be okay. Let's just make sure. So I think we're down now to just solve for T2. So now we can just plug numbers in. Mass of the copper, we said, was 50 kilograms. C sub P for the copper, we said, was 0.39 kilojoules per kilogram Kelvin. And T1 for the copper, we said, was 353 kelvins. Add to that the mass of the water, we said it's 120 kilograms, plus 4.18 kilojoules per kilogram Kelvin is a good estimate for that. And the initial temperature of the water, we said, was 298 kelvins. That whole thing gets divided then by a complex denominator here. It's not complex, but multi-term denominator. But a lot of the same terms. The mass of the copper, 50 kilograms, times the C sub P of the copper, we're saying is about 0.39 kilojoules per kilogram Kelvin. Add to that the mass of the water. It's 120 kilograms of water roughly, and 4.18 kilojoules per kilogram Kelvin. Use brackets on that. Okay. Alright, so it's going to be 50. Nope. Actually, I'm going to do the denominator first, since I'm on just a standard scientific calculator. How do I do this? I might actually do terms here. So let me just simplify, since I'm doing it on a simple calculator, and my other calculators just don't show up good on the screen, so I'm going to have to do a few more steps. But this is a calculator, like a calculator you couldn't use your phone on an FE exam, but a calculator like this works just fine for your FE, your Fundamentals of Engineering exam, so you do want to be comfortable using a standard non-text entry scientific calculator. So I've just multiplied these three numbers together. What's that? That's left in kilograms go away, kelvins. Okay, so I'm left with kilojoules on top. Okay. Add to it this one. That's 120 plus 4.18 times 298. That is 1365.64. And again, as we've talked about before, you guys should have your calculators out, taking notes, just like you would be in a lecture with me. Otherwise, if you're just watching me do this on the video, I can't help but think it's going to be really boring and you're probably not getting much out of it. So try to stay engaged as you go through. Trick your brain into thinking this is important. So I've taken 50 times this 39, or I'm sorry, 50 times 0.39. That is 19.5. The units there are kilojoules per Kelvin, right? Because the kilograms go away. I'm going to add to that then 120 times 4.18. That is 501.6. Again, kilojoules per Kelvin. Okay, so then I'm just going to add those. So notice what happens to the units. The kilojoules are going to go away. I've got per Kelvin in the bottom, so Kelvin's going to go to the top. So we're good. So let's do the denominator. That's 19.5 plus 501.6. So the bottom is 521.1, and the top is going to be 6883.5 plus 1365.64. So the top is going to be 8249.14, and the units left are going to be kelvins. So that's equal to, right, so divide that by 521.1. No, got really close. I saw it right as I hit the button. Divided by 521.1. That doesn't seem right. Okay. 8249.14 divided by 521.1. Okay. I have a mistake somewhere. So I'm going to ferret out my mistake. I'm going to take a break here, which is okay. I've only got about a minute left anyway, so I'm going to take a break here. I'm going to try to figure out my mistake. That is way too low. So hopefully you've already found my mistake and you know before I get back. Anyway, loud pop, and we'll be back.